Okay, well, let's talk a little bit about why we want minimal sum of products. Seems to be good because that's the smallest implementation. Okay, so here's the same truth table, and what I'm doing here is showing you a logic diagram. Now, in fact, suppose I have A and B both high, and I have a input. The C input goes from going from 1s to 0. Well, you can see that if A and B are both high, the output is destined to remain high no matter what C is. And we come up to in a situation where it doesn't matter. If A and B are true, the output of this gate will be 1. But with this logic, independently of the value of C, with this logic implementation, though, when I change the value of the C input, because I'm changing which of these AND gates is on, there's a period of time, as C goes from 0 to 1, there's a period of time, and it has to do with the delay of that inverter, when both of the AND gates are off. They're both producing 0, which means that I get this little glitch on the output. And you can sort of say, well, that's okay, Chris. The TPD of this gate is, out here somewhere. And in fact, if I waited for after the C input changed, if I waited for the appropriate TPD, I would in fact get a 1 on the output. In some sense, you shouldn't get all upset about this glitch. And the answer is, well, officially, I'm not upset about the glitch, but that glitch represents, charging and discharging. There's some power supply, some power dissipation things I might want to do. And in general, maybe I want to figure out how to get rid of the glitch at this level. And you'll see in another lecture why getting rid of the glitch for this particular circuit is hugely important. We're going to use it in a very special way. But for now, just think of it as an academic exercise. What I'm going to do is I'm going to add a third AND gate. I'm going to pick 2 more and build another product term out of 2 more sort of rows in the truth table here, and build this. This particular implementation involving these 3 product terms is functionally equivalent. The truth table of both of these circuits is the same. Y is the same. The advantage is that this circuit has no glitches when C changes. Okay, and it's removing these glitches, a glitch-free circuit, so that a single change in the input that results in no change in the output is guaranteed to have no glitches, is a circuit that we'll call a lenient circuit. And in terms of truth tables, what we're doing is we're rewriting the truth table to involve these don't cares. We're identifying situations where a particular input doesn't matter, okay, and rewriting the truth table here to sort of eliminate 2 rows here. So, for example, I can take the case in the first 2 rows here. When C is 0, the value of B doesn't matter, right? So I've rewritten that. These first 4 rows I've rewritten as just 2 rows with a don't cares. So the don't cares are sort of useful to us because they will allow us to implement more compact logic. Well, this truth table that we've been working on all day represents a circuit that we call a multiplexer. This is a 2-to-1 multiplexer. It takes 2 signals and chooses one of them to be the output signal. So that's given, we call that a multiplexer. It has a select line that selects which of the 2 inputs. So it has 2 inputs and a 1 output. Here's a 4-to-1 multiplexer where I have 4 inputs and I need 2 select signals to select which one of the 4 signals will become the output. I see that down here. And in fact, I can implement a 4-to-1 multiplexer just as a little tree of 2-to-1 multiplexers. Now, multiplexers will be really handy, and let me show you one way in which they're handy. Suppose here's an 8-to-1 multiplexer with 3 select signals, and I have an arbitrary logic function here. I've sort of randomly written a bunch of 1s and 0s in the output column. It turns out by using this multiplexer, I can implement any logic function I want simply by wiring the inputs to the appropriate constant 0s and 1s. Okay, and I'm going to select the appropriate row. You can see the 0s and 1s I've chosen are exactly the truth table. What I've done is I can implement any 3-input Boolean equation using this 8-to-1 multiplexer and simply changing the wiring to constants on the input. So this is an extremely systematic way of implementing logic. I can design this circuit and simply change whether I put the inputs, hook the inputs to power or ground. Okay, and by doing so, I can implement any logic function I want, any 3-input logic function I want. So these multiplexers give us a very systematic way of implementing sort of arbitrary truth tables without having to go through all the complexity of building, sum of products and wiring up gates and wondering if I could do with less. I'm paying the complete cost. In other words, I have enough logic to implement every possible Boolean function built into this. Having paid that cost, I get ease of implementation. Okay, so in general, this notion of a lookup table synthesis, yes?
I'm not sure I understand how the multiplexer lets you...
Okay, so the multiplexer is going to select one of those inputs, right? So when all three of these signals is 0, it's going to select the 0 input. If these signals were 1, 0, 1, it would select the fifth input, so forth and so on. Does that make sense? In other words, the multiplexer, the definition of a multiplexer is it chooses one of its inputs to be the output value. So what we're doing is we're using the variables that come into the equation, A, B, and C, okay, as the things that will select which one of these things will become the output. Okay, and so what we're doing is we're saying, think of this as rows of the truth table. We're selecting which row of the truth table to look up the answer. And we've pre-programmed that particular line, that particular input, to have that, whatever the value was in that row of the truth table. So this is a systematic way of implementing a general purpose truth table, and we can change the truth table we implement simply by changing the zeros and ones on the inputs. I'm putting in a lookup table. Now, in fact, there's a whole type of logic family called a field programmable gate array, which in fact implements actually these general purpose muxes. And what you're changing when you program the field programmable gate array to implement different logic functions is you're changing the zeros and ones that are wired to the inputs of the mux. In general, for an n input function, I need a 2 to the n input mux. And so this gets quite expensive for big logic. On the other hand, here's an example of why muxes are universal. And in fact, think about what this is a logic gate, which normally takes about 10 FETs to implement, but which implement quite compactly here in this mux. Things like carbon nanotubes, which are, everybody's sort of hot on these days as a possible way of building pretty neat, very, very, almost molecular slice logic. Okay, I think they naturally implement a multiplexer as the thing that they do quite well. So.